Hub Industrial. So today's going to be talking about his journey into different things. So,
Indeed. Thank you.
yeah, the floor.
Well, thank you everybody for showing up, and thank you for inviting me to chat. So, the title of my talk here, a reference to one of my favorite movies, if anybody catches it. So let's get started. Actually, before I get into it, I was actually going to do a quick survey. How many of you guys are high energy experiment CERN people? Anybody working with high energy group? No? Okay. What about other experimental or theory computational people who write code for their study, their research? Okay, so we've got a couple of people who interact with programming and code as a part of your research, as opposed to, obviously, we all interact with Mathematica or MATLAB or whatever. So basically, what I'm going to go through here, I'm going to do a quick recap of my background. And I can't really talk about life after graduate school without referencing life during graduate school. So I'm going to talk about a little bit of what I did for my research and dissertation under Dr. Saab, and kind of how I transitioned to getting my first private sector industry job and bailing out from academia, basically. And then afterwards, I'm going to talk about the career jobs I've had so far, and a little bit about my current role and the stuff I work on. Mostly, I'm going to try to keep it simple and at a high level, just to motivate some of the points that I'm trying to make about how physics played a role in all of that, or how it continues to play a role in how I solve problems and build things for money. And then I'll end with some reflections in the same vein of things I've learned, things that are different from academia, and things that are not as different as you might think. So my history is, I'm actually a double gator. I did my undergraduate here as well. I double majored in physics and math. And then I completed my PhD in 2017. And somewhere in there, I technically earned a master's degree, but I don't exactly remember how that worked. But obviously, it was between 2010 and 2017. So when I was in graduate school, I was working on my PhD with Dr. Saab as part of the Super CDMS experiment / collaboration. And this was the cryogenic dark matter search. So this was a direct detection dark matter experiment. We were hoping to physically detect dark matter particles in detectors buried underground. At the time, it was in northern Minnesota, and these days, Super CDMS is now at Snow Lab in Canada. And these little particles were called WIMPs, for weakly interacting massive particles. And the idea is that they would come in and impart some energy in these detectors, and we would hopefully be able to realize that it was a particle we were looking for instead of some background noise. The idea with this experiment, though, was that these detectors are extremely sensitive. We can detect energies of tens of keV, so that's a pretty small recoil. And these things are super cooled to obviously minimize some of the noise and whatnot. And we need some techniques to isolate the signal from the noise, right? There's going to be background radiation depositing energy into the detectors, and we need to figure out what's a WIMP signal and what's a background signal. And one of the ways in which we do that is we study the properties of the crystals that these detectors are made out of. And if you understand very well the crystal structure and the physics that goes on inside the crystal lattice, you can model and predict different kinds of energy deposits and what the outgoing electronic signals will look like. And so depending on things like how much energy was collected, the size of the pulse, and the ratio of freed electrons versus lattice vibrations or phonons, give you all kinds of information and hints as to what you're looking at. So to that end, I developed, well, unfortunately, we don't have a lot of CERN people here because I was going to complain about Geont 4 because that's something that the CERN guys use a lot to simulate particle interactions in their detectors. And so what I did was I taught Geont 4, so to speak, about crystal lattices. So when the high energy guys are simulating their detectors and the LHC kind of collisions and whatnot, they have the concept of different materials. And so the particles do their thing and they are going through a material, but this material is a homogeneous blob as far as Geont 4 is concerned, as far as the simulation framework is concerned. And it just has some bulk properties. So it's, oh, it has this stopping distance or this stopping power. So a particle moving through this block of lead is going to occasionally deposit this much energy along its trajectory. And it kind of averages this idea because they don't care about the material. It's always shielding or something. It's a big brick of lead or whatever. And so what I did is I wanted to leverage Geont 4 because it's a well-tested and well-developed and obviously very optimized and efficient particle tracking system. But since we needed to analyze and model the actual crystal lattice of these germanium and silicon crystals, it wasn't good enough to just say it deposits some amount of energy in some number of centimeters or whatever, because these detectors are like this big. So you need something much more precise. So anyway, the whole point here is that I wrote lots of C++ code as part of my dissertation to simulate the detector response and readout so that we could simulate backgrounds, and then we can get like a test radioactive source, put it near a detector and say, oh yeah, that's what it looks like. Good. The code predicted the thing and we took a measurement and it matched the thing. And what this ended up leading to was, it was actually two parts. There was a physics library that actually links against Geont 4 called G4CMP for Geont 4 condensed matter physics. And that library is actually published and released. It's on GitHub. So other experiments and other researchers are using G4CMP. I was just talking to Tarek earlier this afternoon, and he confirmed with me that people are actively still using it and developing it, which is very exciting for me. It means it wasn't a waste of time. But yeah, so it's kind of a generic framework for defining crystal lattices and the crystal properties in these bulk materials. And so I released the C++ library, which taught me all kinds of stuff about writing code to be shared with other people. It's a little different when you're writing your own code to just crunch some numbers and you can do kind of hacky, junky stuff, and it doesn't matter if it crashes sometimes, and you get your results and you move on. But this was a little different because we wanted intercollaboration contributions, and we wanted other people to add more and more physics processes or more materials, different crystal lattice definitions and whatnot. So it exists on GitHub. It's public. It uses an open source license. But anyway, so I'm doing that. I'm plugging away at my research. I'm down in the basement, sitting at a laptop or sitting in front of a Mac or something. And then so I defended in 2017. So somewhere in the end of 2015, the early part of 2016, a friend of mine reaches out to me. And this friend of mine, there's a little bit of a backstory here. We were roommates when we were in undergrad. He was a math major. I was a physics major. We were good buddies, into the same stuff, played the same video games. We both were avid Magic the Gathering players. I see some smirks. I hope you sought treatment for the addiction. But anyway, when we graduated, I stayed here to work with Dr. Saab on Super CDMS, and he went to U Chicago to do his PhD in biophysics. And specifically, he was doing research on simulating protein folding. And so we actually kept that kind of in common. Oh, cool. We're both doing computational things. We both enjoy, writing the code and simulating stuff and seeing results from that. So we would commiserate about our work. And so anyway, he contacts me in like 2016-ish, and he had finished his PhD. His went a little quicker, I'm going to say, because it was easier. I don't know or really think that that's true, but he finished like 2 years before I did. It's different programs, so maybe it means nothing. But one of the professors that he was working with was on the board of directors of a tech startup in Austin, Texas. And he reached out to me and he said, "Hey man, are you done yet?" And I was like, "Well, no, I'm not." No. So sorry, I skipped ahead. So he reached out, he was telling me about this company. It was called Litmus Health. And what they were trying to do was help clinical researchers. So remember, he's doing biophysics, so he's working with some physics guys, some math guys, some biology guys. And some of these biology guys were medical researchers doing clinical trials of different treatments for various ailments and things of that nature. And it turns out that if you have, a bunch of physics guys who have a lot of data, there's somebody nearby who knows how to deal with large amounts of data, who knows how to write code and wrangle things. But medical researchers at the time anyway, it's a little bit less. There's less overlap, right? With the programming nerds and the math nerds and the physics nerds, we're all like this. The biology guys are kind of over here somewhere. So the idea with this company was that there would be a data platform that would allow clinical researchers or biological researchers to not have to deal with large amounts of data and figuring out how to store and retrieve and run their statistics and analysis on these things. And so it sounded interesting, but I was like, yeah, but I'm not done with my stuff, so I don't know what I'm going to do here. But he invited me to just shut up and go and talk to these guys. And so I went out to Austin, Texas for a long weekend, and I met the people with this small startup. And apparently they were so charmed by me or whatever that they said they really, would like me to join the team, even though I still had other obligations. And so that was the first time I was paid to write code, unless you count, the stipends we get here, but I don't. And what they allowed me to do was in my last year, basically, of my PhD work here, I was able to work on contract, working on their back end systems, kind of cleaning it up. Because remember, this is a startup, so startups are fast and loose with everything. There's not really a whole lot of like automated testing and kind of robust stuff. So like my job being a little bit of the lower priority stuff for them, because I wasn't really going to be able to dedicate my full attention to it, was to go on the back end and kind of optimize some things and write some integrations with different devices that these researchers were using to try to collect data on stuff. And that meant that I got paid, and so I did not have to be a TA or an RA, and that was kind of nice for my last year to not worry about grading lab notebooks and things like that. So eventually I finished. And then, of course, pointing at the wrong thing, I continued working for Litmus Health after that. And so here's their little marketing blurb. Litmus Health provides end-to-end solutions for clinical trial data capture, monitoring, and analysis. We are research-ready infrastructure for wearables and sensor data. Our goal is to help researchers increase the certainty of their conclusions and describe the full value of their digital clinical trials. You can tell it was written by a marketing person. They were very good at getting the right people to make cool logos and write stuff. But basically, some of these researchers that were actually using the platform were trying to integrate various sensor data. So back then, the Apple Watch wasn't out yet, but there were things like Fitbits. And so sometimes people would want to see how, if they recommend, I don't know, regular exercise or something for some chronic pain condition that somebody was having, they could kind of verify it against their Fitbit and run some stats on, oh, how much do you actually move around and what's your pain rating at, whenever you check in to do these surveys. But some of these devices, or many of these devices, you can actually stream a lot of data. So I was working on integrating various devices into our backend system, storing the data, and then finding efficient ways for them to query things or run in-place analysis on the data so that they didn't have to like load it onto their laptop and blow it up because it didn't have enough memory or whatever. That's basically the idea there. So I worked for them for a couple of years, and I got a little bit sick of this startup thing. Most of them were in Austin, Texas, and I stayed here. I was fully remote, which was totally fine with them, but you do kind of miss out when everybody else is in Austin and somebody can just knock on someone's door and say, hey, let's do X, Y, and Z. And then I kind of find out later. It's a little disappointing. So I decided, okay, I'm going to try something else. And so my next role that I found was I went about the more traditional way, I guess, where you just post your resume on Indeed.com or some of these other ones, or apply directly to job postings on whatever the popular websites of the day were. And so, you know, something I want to point out here is that everybody hates software job interviews, and it's always been that way as far as I know, and it's still that way as far as I know, and they have definitely changed, but I would not say they're better. People keep trying different things and everybody hates all of it. So it took a while. It took a few months, which I guess in the scheme of things wasn't that long. I've heard definitely worse, but it took like 2 or 3 months before I actually got a couple of interviews. And every interview is totally different, and they're all bad for different reasons. Some of them will actually give you homework. They'll say, oh, here's some code and there's a bug in it. Find it and fix it or something. One of them that I did was actually like a live pair programming session, where they would give me some code and basically just watch me try to figure it out live, which I hated. It's like, I can't even read with somebody looking over my shoulder, let alone like try to debug some stupid Java program or something. So I didn't do that well on that one, but that's apparently very normal. As I've been doing this for a little while now and feeling older and older, every time I look at these slides and say, oh yeah, I defended in 2017. Geez, that was a long time ago. It's totally normal to get rejected, or to get partway through an interview process and then they just never talk to you again. It's like, oh, you did the first phone interview and then we scheduled the next one and then nothing. So it just happens. So I guess, as demoralizing as it is, the moral there is like, don't give up or don't beat yourself up over it. Even us people with fancy PhDs sometimes just get looked over. So anyway, my next position was with a company called Hub Industrial Supply, and they're a subsidiary of Applied Industrial Technologies. And so Applied is like one of the biggest companies you never heard of. They kind of do like a bunch of industrial stuff. So like hydraulics or robotics, various hardware and supplying stuff. It's not terribly important what they do, but the idea is that I was hired to work on a product that they were developing called Inventory IQ. And again, this is not that interesting to this audience, what it actually does, but I need to explain a little bit about it to kind of motivate some of the points in the lessons later. So the idea they had for this thing was, okay, we sell a bunch of stuff. We sell hydraulic hoses, we sell pumps, we sell safety equipment, safety goggles, nitrile gloves, all the stuff. If you guys work in a lab at all, like somebody has to stock this stuff and somebody has to order it. So you can use this solution, this Inventory IQ solution, where you can keep track of your inventory. You can be alerted when things get low and maybe there's some regulatory reason or OSHA reason you need to always have these safety things on hand, or you can't do whatever it is your manufacturing facility does. And so you can track like spending, and it integrates with different vendors. So you can automatically order things as they get low. You get the shipment tracking, and then it can be kind of received in very quickly into the system and all that kind of fun stuff. Up here, you can see one of our coworkers demonstrating. So Stuart here is using a fingerprint scan reader. And so you can actually, as part of this solution, it's custom built for each of these large customer facilities. And this is an example of our electronic lock system that you can get if you're a company that, not everybody's allowed to just waltz in and grab whatever they need and waltz out. So you can validate who is allowed in, and then we can also track who went in and what kind of stuff did they take out. So if you notice all of your safety gloves are disappearing really fast, you might find out that Joe is, blowing up balloon animals or something with them, and tell them to stop doing that. And the way it works is, once this thing finally finishes reading Stuart's fingerprint, which you can do a fingerprint or you can do facial recognition or a couple other things, he would pick up this device here that's basically an iPhone in a little scanner sled thing that can scan barcodes, or you can wave it around and pick up RFID tags and stuff like that. So you go in and you scan the things that you need for today's task, whatever that might be. And it will attribute that inventory movement to you. And so the idea here is, okay, this all sounds great. Now, how do you run the system? This exists in some customer's facility somewhere, could be anywhere in the country. And we need to send them some hardware, the scanner, some cameras, if you choose to do it, these locks, if you want to have a locking situation. And then we need to present a web page or portal for some manager to go in and make sure things are going peachy keen with their inventory, or to see, oh my God, we're spending way too much money. Yeah, so that's the idea there. And I keep pointing this in the wrong direction. So this is where I come in. So they said, okay, we need to do this, but we need to build something out to run the system, and it needs to be scalable because we're going to have a lot of data. There's the storeroom itself has a lot of different hardware and sensors and whatnot, and are constantly streaming events into our system. So we know somebody entered the room, somebody left the room, there was motion detected in one of the cameras, somebody took out this thing, or they received this order, or blah, blah, blah. So lots of stuff happening. It's also acts as a ledger, so you know how much you're spending on these, how much money you're spending on these things. And you can track kind of the spending velocity. You can say, oh, well, we bought this many, and this month somebody took out $100 worth of Band-Aids or whatever. And that's higher than usual. What were we doing that made somebody get hurt so often? So for this particular system, that's it. I'm not going to talk that much more about the actual system. I know that's not super interesting. It certainly doesn't feel sciencey. But this part is a little more fun and a little more interesting. So this is the basic architecture, and it's a little bit simplified, but most of the stuff lives on the cloud, right? So basically the cloud means somebody else's computer. So somebody else's computer has all of our data. And when you access the management portal, you're contacting the cloud and this content delivery network and load balancer and all this fun stuff. That's all a bunch of tech jargon to talk to some API. And the API is really where the business logic lives. And it gets the data out, it puts the data in, et cetera. Now, this is the part that's where Stuart Johnson was getting into the storeroom here. All of this stuff lives at the customer facility. And so these are optional components that they may or may not have set up for their system. So the system design, I'm thinking as, software architect over here, how do I make a system where it's flexible and modular, where not everybody's going to have cameras, not everybody's going to want the lock on their thing, not everybody's going to have RFID tags. So you have to design these things so that they're modular. You have to model all of these interactions so that the data can flow and you don't have problems. But it's tricky because this is deployed somewhere other than this. And then you might have vendors that have integration with our system to do shipment tracking and price checking and all that stuff. So those are independent systems. There's more than one of these. This is an example. There's obviously more than one of these too. We have more than one customer. And it's cool because the load balancer here is scalable, meaning that if we get a lot of events, a lot of traffic going on, and our little API code here is getting bogged down, this load balancer will spawn new ones, like a little army of zombies here. And then as things quiet down, it's configured to kind of kill them off until you have the right size for whatever the current payload is. So there's a lot of parts to this, and it turns out there's a decent amount of code involved in putting all those things together. And just from the raw numbers, the whole cloud part with the API and all that stuff is about 125,000 lines of code. The storeroom system, that's the stuff that's actually at the customer facility. We actually use basically Raspberry Pis, what those are, those little tiny computers, but they don't need a whole lot of horsepower for what we're doing because they're mostly just talking to all the peripherals that might be installed in the facility. But even that is almost 60,000 lines of code between figuring out how to get it to talk to the cameras, talk to the locks, then talk to upstream and synchronize the data as data changes in the system. The storeroom might have to know about it. For example, a manager might log into the system and say, oh, we fired Joe yesterday. He's not allowed in the storeroom anymore. The storeroom has to know immediately that Joe's fingerprint doesn't work anymore, right? So it has to get synced and immediately sent to the lock and all this stuff. So there is a little bit of complexity involved in doing that. And then the front end, which is basically the web page stuff, somehow clocked in at 42,000 lines of code, which shocked me at first, but then I remembered how much I hate HTML and JavaScript and how tedious it is. And so I was like, yeah, okay, that's probably about right. But all in all, it's 220,000 lines of code, and we're a very small team. So the idea here, and the whole reason that I went on the spiel about the actual product, is that our job is to wrangle this complexity. And that's where this all comes in, is because actually as physics and mathy people, this is what we excel at, right? We have a model, we have some data, and complexity wrangling is what we do. When you write down an equation, right, we're not remembering a bunch of sets of data. We have one expression or one equation that describes all the sets of data. And so that becomes kind of relevant in implementing these things. So tools and skills, as I guess things that I use every day that are, the practical stuff. If you're here and you're working on code and stuff, especially for your dissertation, and you're not familiar with a Linux or Unix style system and just navigating around the Linux operating system, and you're at all interested in doing stuff with computers, you gotta do that. You're not going to get by with just figuring out Windows C:/ whatever. Everything runs on Linux. Every single web server in the universe is basically running Linux. So you got to do that. Version control. The only game in town right now is Git. Back in my day, when I was young, there were other ones, and Git ate their lunch because it's so much better. So you definitely have to be familiar with Git. And you should be anyway, if you're doing anything at all with code, even for your research here, or even just writing your dissertation. You're going to have multiple versions, and you might say, crap, I actually liked it the way it was before. How do I get back to that, right? And so having version control where you can look at the previous versions and compare works for anything text-based, really. So you should learn this anyway. It's like a super awesome computing life skill. One thing I kind of want to harp on, and unfortunately not so many of you guys are doing computery stuff and programming stuff as I was kind of hoping, because I wanted to kind of rant a little bit about OCI containers. I leverage this heavily when I'm working on this inventory IQ system or any other complicated system. All of these things, I can't really run a lot of this on my laptop, right? But the way this works is that I do have a deployment process that says, hey, boot up a server, a virtual or otherwise server that's running this version of Linux with this version of the C++ compiler or whatever you're doing, right? If something goes wrong and there's a bug and the version of whatever compiler on my laptop is different, I might not be able to reproduce it. And actually, this was relevant when I was in grad school too. I was actually just telling Dr. Saab that I recalled we had published a paper at one point before I graduated, and it had some visualization of some data, it was some histogram, and I used Python and Matplotlib and made something colorful and pretty. And then several months later, somebody said, hey, we're doing another paper and we want to reference that. Can you, generate that image for us again and give us, a fresh version of the file? And I was like, yeah, this is great. So I went over to my laptop and I found the exact data that I was using, and I found the exact Python script that I was using, and I ran it, and the plot came out completely different. Isn't that awesome? And it was because I was running Linux on my laptop. I was installing Python from the package manager, and so something upgraded to a different version, and that version of Matplotlib or whatever it was handled something slightly differently. So now I couldn't reproduce my stupid results because some version changed and some developer somewhere decided they needed to change the behavior. That is where these guys come in, because with these containers, all that means is that you're pretending that your software is running inside an operating system that you define. So you say, I want a container that has Ubuntu Linux version 24.04, and I want these packages installed at these versions. And now every single time you run your stupid Python script, it's going to have exactly that same version, and it's always going to work exactly as you predicted. So I encourage you strongly to investigate this. If any of that made any sense to you and sounded relevant. Yeah.
Is WSL and OCI? So Windows subsystems for
I don't know how that works. I haven't run Windows on a personal machine, thank goodness, for like 20 years. I do know of it. No, I don't like Apple either. This is a work machine. This isn't even mine. I'm Linux bare metal all the way. But I don't actually know how it works. As far as I don't think it is. On Mac,
It just sounds very similar.
it is similar. I think Windows is actually, I hate to give them credit, but credit where it's due. I think they are actually running even closer to the metal when they run their Linux kernel in this weird subsystem for Linux thing. So I think it's actually even faster and more performant than when you do this. You will notice performance degradation. So you're not going to do heavy number crunching probably in one of these guys. You're going to have to find a way to bridge the gap there. So maybe just, have the code or something that generates the plots or whatever. And it depends. On the Mac especially, there's a big slowdown with these, but if you're running Linux bare metal, it's native speed. You're getting 100% performance basically. Even saying, oh, I'm running Red Hat Linux, whatever, I want a container with Ubuntu Linux, it's still running at native speed. You're good to go. If you're on a Mac like this computer, then you get a little bit of a slowdown. But anyway, other things that are important here, automated testing, sometimes we call it unit testing, but that term is so overloaded and people disagree on what it actually means and what counts as a unit. But any kind of automated testing. So it's not good enough to write some code and just open the web page and poke at it and say, oh yeah, look, it works, cool. Especially when, we're dealing with people who are paying us a decent amount of money. They don't want bugs. So we try to automate things. And then the last part is you have to write good code. And that's the most important part. And that's where wrangling the complexity comes in. And so for me, I do genuinely believe that my background in physics here motivates how I think about these things. And maybe you'll agree or maybe not when I ramble about this next part. It's all about modeling, abstraction, and reproducibility. The reproducibility we get from the containers, we get from the automated tests. So if you change code later and the tests start failing, you screwed up, you roll back. But it's the abstraction part that's kind of interesting. And so I'm going to give you some code tips. And it's going to be very, very brief. I'm not going to go in depth. I'm just going to be a little bit obnoxious here and get on my soapbox. there's something called functional style programming. And there's different styles. Programming languages are not typically very opinionated about what you do with them, but you can enforce kind of your own rules or paradigms for how you're modeling these things. And so from Wikipedia, which is, the best source of all information, functional programming is a programming paradigm where programs are constructed by applying and composing functions. Okay. The important part here, function definitions are trees of expressions that map values to other values, rather than a sequence of imperative statements which update the running state of the program. So what does that mean? It means the Math 101. A function maps things from one type of value to another type of value. And believe it or not, that's not a given when you're talking to programmers, okay? So here's an example of a non-functional function, which sounds silly. I'm doing a test. Is it afternoon? And you're going to get a Boolean value, true or false, right? And so according to this function definition, I have no inputs whatsoever. So I don't have to give this function any information, and it's going to tell me whether it's before or afternoon. How does it do it? It grabs the local time at this moment that it runs, and it says, is the hour greater than 12? All right, okay. But this is not functional. Why is it not functional? What's the input? Well, there's input, but it's lying to you about what it is. It says there's no input, but there is, right? It's the local time, which is like the state of the universe here. So this function is reaching out outside of itself, and that's hard to compose. When I'm dealing with 220,000 lines of code, and I look at a function that says, oh, cool, I don't need to give you anything, you're going to give me a value. It sounds great until I remember, actually, there is input. And I have to figure out what it's doing. And I don't want to have to go into the function definition to figure out what it's doing. I'm trying to work at a higher level of abstraction here. So what I recommend you do instead is you make the input explicit. Now you have a function that is mapping local times, x, to Boolean values, y. This is a pure function. We sometimes call it pure, meaning it has no side effects. It does not depend on the state of the universe. It doesn't reach outside. Everything is in bounds here. All the data it can see, you give it. All the data it returns. Now it's deterministic. Now it's easy to test. It's easy to debug, and it's easier to reason about. In the same vein, we have the concept of partial and total functions. Basically, a total function is kind of what you expect. It maps values from x to y. And if you took any kind of group theory or abstract algebra, some of these things might be a little familiar, maybe even trivial. But a total function will map every value of the set of x to some value in y. A partial function only maps some of the values in x to some set y. And so here's an example of a partial function. This is a really stupid example, but it's just to motivate the point here. This function maps the set of pairs of integers to integers, but it's not total. Why not?
Some pairs of integers that result in none.
Correct. And tell me about it. Which ones? What's the problem pair or set of pairs? What's the problem here? How do I not get an integer out of this if I'm dividing an integer by an integer?
Denominator's zero.
Yeah, right. So this function is partial because it says that it takes a pair of integers and gives me an integer, but it absolutely will not always give me an integer if one of these happens to be 0. It's going to blow up my program instead. So when I'm, again, working on 220,000 lines of code, and I see a function that I want that has a cool name that does the thing that I think it should do, and it's telling me that it takes 2 integers and gives me an integer, and I want an integer, I say, oh boy, I'm done. Submit, commit, we're good to go. Then it crashes in production and the customers get mad. What we can do, there's actually several options you can do here. In one case, I force it to be total by returning some special value. So now this notation here means it can be either an integer or the special value null. A lot of programming languages treat null value as special. So I can choose to rewrite this function, it's not going to be a pair of integers to integers because you just can't do that with this particular operation. But I can map a pair of integers to the set of integers or null. And that may seem trivial and it may seem silly, but now when I go to write my code and I go to reach for this function, the compiler will not compile code if I pretend like this was always an integer. So if my next line of code is this plus 1, it will not compile. I have to explicitly handle the fact that it could have been some other value that's not an integer. That makes my job of designing these abstractions and writing these APIs and fixing bugs much, much easier. Now, this all sounds silly, and you can say, well, duh, you just remember you don't divide by 0, you know, so. But the problem is, again, when you're working at a certain level of abstraction, you don't want to have to change gears. When you're doing your thermodynamics homework and you're writing PV equals nRT, you're dealing with macroscopic quantities. You're dealing with volumes, pressures, whatever. You're not thinking about an individual helium atom bouncing off and wondering what its kinetic energy is and what direction its velocity vector is, right? You want to operate at the same level of abstraction, and this helps in wrangling the complexity. Think in mathy terms, write your functions as explicitly and as purely as possible so that you don't have to worry about remembering a lot of stuff. Psychologists will tell us that the magic number for working memory is 7 plus or minus 2. That's how many things you can keep in your working memory. So the only way to deal with complex things is to compress the complexity. Take several things, put it into one. I don't have to think about anything when I call this function because the compiler will yell at me. I like that. I don't want to have to think about anything. I don't want to have to remember. I've got precious 7 plus or minus 2. For me, it's closer to 5, I promise. So I don't want to have to remember more stuff. It's not going to work out well. So that's the end of my rant part. But basically, the idea here is that even when I'm writing software, I still feel like I'm doing kind of mathy, physicsy stuff. You're modeling things, you're designing systems. That system diagram I showed did not exist before I was hired to build the thing. So you have to kind of figure out what is it that we're trying to do? What is it we're trying to model in code? And how do we do that? How do we separate out these things so that they can act like black boxes that I don't have to remember the details? I don't have to remember 10,000 lines of code to know how to interact with a database or whatever. And that's what physics is really, really good for. We are good at drilling down to the fundamentals, really understanding something very deeply, and then building on top of that. That's the thing. You go to the fundamentals and then you build on top, and you have to write good abstractions. You have to model things well. And then, of course, drawing the correct conclusions from information is also an interesting conundrum that sometimes we struggle with. When we have a bug or something, it's not infrequent to have people assume that it's coming from one part of the system. When you're more familiar with it, you might think, well, there's actually maybe another way that this bad data could have entered the system or whatever. And I think that we're pretty good at figuring out what are the edge cases whenever you're doing your physics homework and you're deriving some equation, and you can make some approximation. That's great, but then you remember where you made those approximations and you change your expectations accordingly. Some of the things that you kind of have to learn outside of just saying, yeah, physics teaches you everything and makes you good at everything. It doesn't necessarily. This is the one that I struggle with still. I want everything to be correct. I want to model it perfectly. I want the code to exactly represent all the constraints that I think the system has. And usually that's not really tenable, especially because in these systems, the model evolves, right? So if you're talking about, science and you're trying to figure out what's the relationship between this quantity and this quantity, there's one right answer. Whether we can figure it out or not, the universe doesn't care, but there is an answer. In this case, there's not always a right answer. And even if there is a right answer, man, they don't care as long as they can sell something, right? So I'm trying to model these things like perfectly and make them 100% optimized. And they're like, well, does it run quick enough? And I say, yeah, but it's the wrong algorithm. It's the wrong data structure. This would be such a better match. Nope, ship it, done. It's a struggle for me. And this is what I was just saying, is that it's the changing requirements takes getting used to. And sometimes you have to stop partway through something. You're developing something, and then somebody says, no, wait, actually, how about if it does this? That can be a little frustrating isn't always the right word, because it's not necessarily a negative thing, but it requires getting used to being able to change gears. And then this communicating with non-experts, there's actually two meanings kind of here. So first of all, you might have to talk to other people in whatever industry or business that you're working for. So like I'm right now working for this industrial supply company. And so, these are not always tech people. They're people working in some of these facilities. They know their business very well, but they don't necessarily know about tech very well. Some do. So communicating what the system does or how it works or whatever, you really have to develop an ability to know your audience and to remember what you didn't used to know. It's easy to, especially in an environment like this, where you're all, you get into a research group or whatever, and you have all this jargon. It can be really easy to forget that not everybody speaks that language. Not everybody says means the same things with the same words. But also communicating in this case can also mean the users of your software. So like you saw, we have a web portal that people have to log into to look at their inventory tracking or graph their spending limits or whatever. That's communication as well. And so when we're thinking through the software part of it, we're asking what workflow makes sense for the most people, and how do we present that to them so it's not confusing, or there's not too many things going on, or that things are, on the opposite side of that, not too hidden. And so that's also a struggle. It's something that takes a lot of work and that I haven't quite perfected yet either. But it's stuff you got to do. So miscellaneous advice. I'm going to reiterate: use version control, learn Git. And in fact, you really should, again, revisit those fundamentals, learn how Git works. What if you don't know what the index versus the head is in Git, read the manual. You should really understand it, because you can get yourself into some trouble with Git too and totally screw up your workspace. Usually it's okay, because you can just blow it up and re-download it from somewhere else, like GitHub or wherever you send it. But it's good to know how it works under the hood. Same thing with containers. I really recommend anybody who's running code or generating plots or whatever, or just you need to share it with somebody else. I was part of Super CDMS, which was a fairly big collaboration with people all across the country, and actually across a couple of countries. And so we had to share lots of stuff. So we did use a lot of version control stuff. At the time, containers weren't as prevalent, and I wish that they were, because it would have made a lot of things easier. I don't know, I didn't ask Tarek this afternoon, but I kind of hope maybe they are using some of this stuff. And then, I like to, in my head, I'm modeling mapping things. I have this data, I need this data, I'm applying transformations. I'm not worried about the exact lines of code. Once I'm done writing that function, I never want to look inside those curly brackets again, right? I just want to know that it works the way it's supposed to work. But also at the same time, going too fast and heavy on trying to find an abstraction or a model can bite you in the butt too. And that was something that I did early on in this inventory IQ thing. Was I really tried to nail down, some very precise models and abstractions, and it turned out to be a little brittle, because I didn't really account for the fact that things change all the time in real life and business and whatever. I was thinking like I'm coming up with the grand unified theory of inventory tracking. And it didn't work out, because it just keeps changing. So now I've figured out, this is earned wisdom that comes with just experience, figuring out, okay, that's probably likely to change. So I'm not going to put quite as much effort into making it into some really cool, slick API where you only have to call like, 2 different verbs or something. And then this last one is kind of a little tongue-in-cheek. In grad school, at least for me, I learned a lot of humility. I was, used to knowing a lot of stuff and, being kind of a smart guy. And then, I started doing PhD stuff where I took a semester of quantum field theory and that went out the window. And I thought, wow, okay, there's a lot of stuff I don't know. But then it kind of ebbed a little bit the other way. You'd be surprised how low quality some code is in the real world. If you think like, wow, this sounds really intimidating. I don't know if I can, get used to all those semicolons and curly brackets and whatever. I'm telling you, I've seen some really bad code, and people who are making money writing this code that I'm just like, so, but this has a practical aspect to it as well, in that a lot of times people will tell you, no, don't implement that algorithm yourself. Somebody has a library that you can just roll into your project and it's already done for you. And I'm telling you, unless it's something extremely complicated, there's a lot of things you're better off just writing yourself and testing yourself, and it works, because there are all kinds of surprises where you're like, wow, I didn't think anybody could screw that up. But it does happen. And my most important piece of advice is that since this is about life after grad school, don't forget about the life part. There are more important things than what you do for a paycheck. And that's it.
Okay, so we're gonna open up to any
Questions?
Also, people on Zoom, if you have questions, you can send in the chat or raise your hand and maybe I'll let you.
As far as like resources for learning, like, because you're talking about some fundamental stuff too.
Yes.
Do you have anything that you recommend, or is it kind of just like, find a tutorial and just go through?
That's tough. Honestly, yeah, find a tutorial is pretty good advice. You know what I will say though, is that installing Linux on my own laptop and using that as my daily driver went a long way towards just being able to manage that stuff. If something's going wrong on one of our servers, it's immensely helpful that I'm very comfortable just secure shelling in and navigating around and manipulating text files and all that junk. Even if you want to sit here and pretend like Mac OS is a Unix, which I know technically it is, but if you never open the terminal and use the command line, then it doesn't count. You had a question.
Not when you're not doing I do miss.
I do miss it. It's funny because I think when Marie, one of our emails back and forth, a word that she used to describe this when I asked, like, okay, cool, what do you want me to talk about? A word that jumped out at me that stuck with me was the word candid. So I'm going to be candid. I'm going to tell you, I miss doing science. Some of the stuff doesn't sound that cool. And I do enjoy the work because I enjoy the puzzling and I enjoy the modeling. And that's honestly the same thrill that I was getting with Super CDMS is, I'm modeling these detectors in code. I'm writing these physical processes and I'm running tests and seeing the data and it matches. I get the same feeling when I'm running against some stupid inventory ledger or whatever. But I do miss, getting to talk about dark matter and stuff. Like that's way cooler. Well, I'm not that old, so I'm contributing to something scientific is still on the horizon. And in fact, I did actually not lately, but I was still giving advice for G4CMP for a number of years after I finished. And I do contribute upstream to open source libraries or things that we end up using in our system. And some of them are not totally boring. Some of them are a little like mathy and abstract and stuff. When you're doing, especially like we do have, some people's, at least their names and some personal information, and we have to make sure it's secure. And so I do actually, I've taken several courses on cryptography. And so we have to make sure that we understand well what the flaws are in different encryption and hashing algorithms. So there's some amount that I can say, okay, I still feel a little academic here because I'm reading some equations and some, some mathy stuff. So I don't know. That part does still thrill me, and I would like to contribute more to that kind of stuff. But I'm not going to say I regret it. The lifestyle was a big motivator for me. I didn't really want to have to do several postdocs and moving across the country every 2 to 4 years for however long, and then being a professor somewhere and getting, another however many years before you get tenure. I don't want to be 50 before I figure out like if I'm settled somewhere.
I don't know if you already answered this or not. But
That's fine.
so that's your, like, when you're trying to like apply for like your job like outside academia, how do you feel that your background is compared to like a computer science?
Yeah, no, that's actually, that's a good question. I don't know about compared to computer science because I don't have that background, but I will say that depending on I used to feel a little self-conscious almost, or almost like sketchy about tailoring my resume to the job. Absolutely don't feel that way. Do it. You have to pretend that you were made for whatever job you're applying for. Not to say lie, but focus on the things that are relevant and really just don't focus on the things that are not. And in this case, with these academic backgrounds that we have or will have, writing that you have a PhD when you're applying for, creating some back-end system for whatever is not usually very relevant. And I wouldn't say that it did me any favors getting my most recent role. It certainly did my first role, but for multiple reasons. And partly because it lended credibility when I was talking to the researchers who wanted to use the system. They'd say, oh, good, he's a science guy, he gets it, he knows how to do research. That was extremely relevant, but not every role is going to care. And so you should just tailor to what you're looking for. Did that answer that?
Any more questions? Yeah.
Yeah, so going back to some of your comments earlier about tech interviews and the fact that
Yeah.
no one really does it right. per
Yeah,
se.
yeah.
I do know that there kind of are sort of a number of standard things that people use to try to at least prepare for them as best as
Yeah.
possible, like lead code, for
Yep.
example. I know is one.
I did a lot of LEET code.
I was gonna say, did you go through that
I did,
experience as well? And do you also have any other advice just about that whole process? And
So I do have a semi-related piece of advice. First of all, I will say I did do a bunch of LEET code, and when I was actively looking for stuff, I made sure that if somebody asked me to do a breadth first search of a B tree or something, data structure, that I would be able to. I could not if you asked me to do it right now. It would take some time. But that's why I also didn't do well on that one where they were watching me work. But the tangential piece of advice there is I would say whatever you're doing, even while you're doing your research here, if you're at all interested in industry or private sector stuff, write down the things that you've done. Log it somewhere. Whenever you do any kind of interesting technical thing, even if it's just implementing some algorithm or something, write that down, because that's the stuff that they're going to want to know. So you're going to want to share with prospective employers. You're going to want to say, we used to do it this way, or this thing didn't exist, and then I wrote some code and now it does this, or I implemented an algorithm and now we solved this problem or whatever. But write down like concrete things that you actually did or made, not so much I learned this, because that's the part that is a struggle for them, because people do bluff and lie about what they know. They act like everybody wants to seem like an expert because you want to be hired, and the companies know that. So it's an arms race of lying to each other and trying to trick each other, I guess. I don't know. It is a frustrating experience. I'm not going to lie, but you go in knowing that, and it probably stings a little less.
Any more questions? Okay, I have a question.
Yeah.
So, I'm curious, to what extent you use AI in your job? And then also your opinion on how it's gonna affect jobs for software developers, current ones, but also for us, for people
Right.
who are entering the job market.
Yeah, I mean, I wish I could tell you that I had a good reason to make a prediction.
It's fine. It's just like if you have any insight
But
or just
so
what you're currently experiencing.
I will say I do use Claude Code daily. I will say that the vast majority of that 220,000 lines of code was written before Claude Code was a thing. So the fundamentals don't change. You know, I treat these AI tools as a force multiplier. I do not let it generate code that I don't understand or that it kind of has its own idea about. I don't check in code to our repository that hasn't been reviewed by a human being. Claude, as much as they improve and as quickly as they've been improving, I'll tell you, even a year ago, I wouldn't have said that it fundamentally changed the way I work. Sometimes it was helpful to generate, especially if I ever had to touch the front end stuff, which I really, really hate. So if I had to do something with like throwing some HTML up somewhere, it was awesome. But beyond that, it was pretty dumb. And even more, but more recently, the last year or so, they've gotten a lot better. And I think, I don't know, it's hard to know if they're going to keep getting that much better every time, or if there's some plateau we're going to hit. But I do. Right now, we're in the middle of a hype cycle with it, right? And so right now, everybody's really, really banking on these things, just replacing most developers. And somebody still needs to steer these things. I literally am still interacting with Claude Code, and I'll say, you know, okay, Claude, you know, make a thing or test this code I just wrote or whatever. And I'll watch it sit there and it'll write some test code. Then something won't pass the test and it will delete the test. It passed all the tests. So you got to babysit these things. You know, there's stories online about, oh, I bootstrapped a whole business by getting a bunch of hallucinating robots to talk to each other. And you have to remember that most people on the internet are not people. Like that, it's all lies and stuff. So I don't know. That's all bots and stuff. So who knows? They're all paid by Anthropic or somebody to say they're doing awesome things. But I mean, I do know people who leverage them and get a lot of value out of them, and we are getting a lot of value. But again, it's a multiplier. It's not changing the fundamentals. We still need to have good abstractions for these distributed systems. You still need to understand the business goals, and Claude doesn't understand the business goals, and it doesn't understand what compromises, you know, are acceptable or not. And it certainly doesn't understand that make it pass the tests doesn't always mean you can delete the tests. So, but as far as like hiring, I know right now the job market is rough.
Yeah.
But I do genuinely think that that's because we're in this hype cycle and everybody just hopes that they'll get to stop paying humans. But I am skeptical, and I think it's going to be like, you know, the .com bubble, where obviously there are still websites, even though the bubble burst in 2001 or what, you know, whatever it was. So AI is not going to go away, but I don't think developers are going to go away either.